이제 마지막으로 두 편의 전문가 강연이 남아 있습니다. 이어지는 세션은 그린테크 세션입니다. 데이비드 롤릭 밀라 맥길 대학교 조교수님께서 머신러닝과 AI를 이용한 기후변화 대응책에 대해서 강연을 펼쳐 주시겠습니다. 해외 현지에 계신 관계로 영상으로 만나 뵙겠습니다.
Hello, everyone. I'm very happy to be here. I'll be talking about tackling climate change with machine learning. The problem of climate change does not need much introduction. We are increasingly seeing its effects. The average temperature is going up, and extreme weather events are increasing. More and bigger storms, floods, droughts, heat waves, fires, or other effects, depending on where in the world you live. The past few weeks alone have seen historic droughts in China, East Africa, Europe, and parts of North America, at the same time as historic flooding in Pakistan and Korea. Many people have already died as a result of climate change, but just how bad it gets depends on what we do now. Climate change is happening because humanity has increased the amount of greenhouse gases in the atmosphere, mostly carbon dioxide, methane, and nitrous oxide. And it will continue to get exponentially worse until we reduce these greenhouse gas emissions. If net emissions do not reach zero by 2050, the science tells us to expect truly catastrophic effects. Action against climate change means both mitigation, reducing greenhouse gas emissions, and adaptation, resilience to the effects of climate change, like floods and storms. Where do AI and machine learning come in? A couple years ago, I led a multidisciplinary team of authors in writing a paper called Tackling Climate Change with Machine Learning, which gives a detailed taxonomy and analysis of the different ways that machine learning can be used in climate action. In the full paper, we identified opportunities for ML to play roles across different areas and sectors, from electricity systems, buildings, and transportation, to land use, climate prediction, and societal adaptation. While there isn't time here to go through all these applications, I wanted to highlight a few themes we identified for the kinds of impact that ML can have, which cut across different areas of application. I'll go into each of these themes with examples in the next few slides. Distilling raw data into actionable information, optimizing complex systems, improving predictions, accelerating scientific discovery, and approximating time-intensive simulations. Okay, let's dive into the first theme. There are many ways in which ML can help advance climate action by taking some huge raw data set and going through it to pick out actionable information, which might be too slow or cumbersome for a human to do at scale. Often in these situations, the raw data is a set of images, for example, satellite or aerial imagery, or a corpus of text. And so computer vision and NLP are often relevant. One example of where this role for ML comes up is in mapping deforestation in real time. Increasingly, machine learning is being used to parse satellite images to work out where forests are being cut down for agriculture, timber, or mining. This can be valuable in guiding policy decisions, as well as interventions in cases where forests are protected. Mapping deforestation is also useful for verification in carbon markets, where landowners get financial benefits if they can prove that they're conserving their land. Mapping carbon stock is a related task where ML for remote sensing is also being used. This means quantifying the amount of carbon that's stored in a forest, a grassland, or another area of land in order to better determine the value from an emissions perspective of preserving that land. Another setting in which ML is being used to parse raw satellite data is in gathering information on buildings. There's very little publicly available information about what buildings are where and how much energy they use, which makes it difficult to shape policies. Using computer vision, it's possible to approximate the footprints and heights of buildings from which their energy use can in turn be approximated. These are both examples of tools for climate change mitigation, reducing greenhouse gas emissions. Now let's look at some examples from adaptation, responding to the effects of climate change. ML has been used, for example, to correct errors in global elevation maps so as to pinpoint coastal communities that are at risk from flooding. By working out the exact heights of different areas, these algorithms have made it possible to determine that hundreds of millions more people are at risk than had been previously thought. As an example from NLP, there's a lot of information in corporate financial disclosures that can be useful in informing climate policy decisions. For example, what risks companies anticipate from climate change. Training NLP models to pick out relevant passages has sped up the process of finding this information. Overall, we've seen ML algorithms to be very useful in distilling big, raw datasets into actionable information that can guide policies or other kinds of decisions. Moving on to our second theme, let's consider settings in which ML can help operate complex automated systems more efficiently. A wide variety of algorithms can be relevant here, from classic optimization techniques to reinforcement learning. ML is being used to control heating and cooling systems more efficiently so that they use less power. This is true both for smart thermostats in personal homes and also in the more challenging cases of large buildings and industrial processes. Increasingly, ML is being used to help optimize transportation schedules. For example, the train timetable of the German railway operator Deutsche Bahn incorporates ML. This can also help in allowing different modes of transport, such as trains and buses or trucks, to interface smoothly for public transportation and freight. ML can also be used to reduce energy in industrial processes like steel manufacturing or cement manufacture, which together are responsible for over 10% of global greenhouse gas emissions. Note that in situations where ML is being asked to optimize a system, the objective function is very important, and in particular, it's not always aligned with climate action. For example, reducing cost may end up reducing greenhouse gas emissions, but not always. It's also worth noting that making a process more efficient can sometimes increase the amount that people use it. This is called a rebound effect, and it can diminish the savings one gets from improved efficiency. ML can be helpful in improving predictions and forecasts across many different application areas. A variety of time series analysis techniques can be relevant here, including Bayesian methods and sometimes computer vision techniques in settings with image-based data. As an example, on an electrical grid, the power being generated needs to match the power being consumed at each point in time. Fossil fuel power plants can largely be controlled to vary the amount of power being generated, but for solar and wind, the power being generated varies from minute to minute, depending on the sun and wind conditions. ML is starting to be used to forecast how much wind and solar power will be available, including by using historical time series data and satellite imagery of clouds. This makes it possible to use more wind and solar and less power from fossil fuels. Similarly, ML is being used to forecast the amount of demand for electrical power from time series data. The UK National Grid recently implemented ML algorithms that cut in half the error in their power demand forecasts. As another example, this time relevant to adaptation, ML is being used to help forecast crop yield from satellite images in response to the threat climate change poses to agriculture and food security. Our next theme is accelerating scientific discovery. There are many settings in which new materials or other technologies can advance climate action, but the process of perfecting such technologies typically takes huge amounts of experimentation. In some cases, ML can speed up the process, not by removing the need for physical experimentation, but by helping design new experimental setups. Such algorithms can include generative models, active learning, and reinforcement learning, and where chemical compounds are concerned, often involve graph neural networks. In the case of materials design, ML can be used to learn from the outcomes of past experiments to suggest promising new materials. This can be valuable in the design of new compounds for batteries, photovoltaic cells, and catalysts used in green energy applications. As another example, reinforcement learning methods were recently developed that can effectively control plasma in experiments on nuclear fusion, a potential future source of low-carbon energy. For our final theme, we turn to the ways in which ML is used to approximate simulations. Physics-based simulations turn up in many climate-relevant areas, and while calculations based on known physical laws are highly accurate, they can also be slow, and ML can be used to produce faster, approximate answers. Relevant ML methods can include physics-informed techniques, computer vision, and interpretable causal methods. As one example, climate models are complex ensembles of physics-based simulations of how variables like temperature and precipitation behave around the globe. These models can take months to run, even on powerful computational infrastructure. And even then, climate models normally operate at relatively coarse spatial resolution, such as hundreds of kilometers, since higher resolution can be prohibitively computationally expensive. But that limits the utility of these models in informing local measures for climate adaptation. ML-based super-resolution techniques are therefore being used to increase the spatial resolution of certain pieces of climate models. In a totally different setting, ML is being used to approximate certain portions of car aerodynamics simulations in order to design more fuel-efficient vehicles. And in the power sector, ML can speed planning models used to simulate electrical grids, which are again based on domain physics and can be extremely slow. Okay, we've seen a number of climate-relevant applications of ML across different sectors and fields, with ML playing roles in distilling data into useful insights, optimizing complex systems, improving predictions, accelerating scientific discovery, and approximating simulations. If you're interested in further details, I encourage you to check out the interactive version of Tackling Climate Change with ML, which is available at climatechange.ai/summaries, where you can search for different applications by theme, subject area, or machine learning technique. I want to now go under the hood a bit and talk through the process that we used for evaluating and prioritizing applications when we wrote this paper. There were a number of questions that we found to be very useful in shaping our thinking, and there's still a useful framework for me when I'm considering a new potential project. First, is ML needed to address the problem? There are many urgent problems related to climate change where ML unfortunately isn't going to be helpful. There are also problems that have already been solved without using ML, and where the existing solution is perfectly fine. What is the scope of the impact? You don't have to work on problems that could reduce megatons of carbon dioxide. More modest gains add up, but at the same time, working on, say, reducing plastic straw use may not be the best use of time. It's good to have at least a ballpark sense of how meaningful a problem is from a climate perspective. What is the time horizon of the impact? A ton of carbon dioxide reduced now is much more impactful than a ton reduced in 30 years, since the sooner we can achieve net zero emissions, the lower the damage. This is one reason why planting trees, while important, is generally a lower priority than preserving the trees we have. Similarly, working on technologies like nuclear fusion, which at best are decades away from success and scalability, can be valuable, but it shouldn't detract from nearer-term solutions. What is the likelihood that a solution can be found? It's very tempting to work on moonshots that have some small probability of huge impact, but often it's better to work on problems with a high probability of medium impact. Also, sometimes those moonshots have a long time horizon, which we've seen is less ideal. Can a solution feasibly be deployed? The best algorithm in the world isn't going to have an impact if nobody will use it. Sometimes machine learning works, but isn't scalable in the relevant setting, for example, because of hardware costs, expertise required to run and maintain it, or access to annotated data. What are the potential side effects of deploying the candidate solution? An optimization algorithm might reduce greenhouse gas emissions, but increase other human costs. A system for gathering data on vulnerable populations could be co-opted by bad actors. Depending on the situation, it may not be feasible to avoid all negative side effects, but where possible, they should be recognized upfront and mitigated. Who are the relevant stakeholders who are involved in or affected by the application? They may have constraints or requirements that need to be built into any viable solution. And it is through their eyes that an approach should be judged. I'd now like to highlight a number of considerations to bear in mind when thinking about the overall space of ML applications and climate action. First, remembering that ML is not a silver bullet. It's only one of the many tools we need, and it's not applicable everywhere. It should never replace or distract from other actions involved in tackling climate change. Second, some of the most impactful and interesting applications aren't flashy. For instance, detecting failures in railroad systems doesn't receive as much press as self-driving cars, but from a climate perspective, it's probably more beneficial. We'll talk about this more on the next slide. Sometimes to find those non-flashy problems, you really have to dive deeply into understanding what is needed within a particular area of application. It's also worth noting that while state-of-the-art methods can be useful in many cases, In other cases, simpler methods may be enough. One shouldn't leap to using transformers when linear regression will do the trick. In my own research group, we try to pick problems where we think ML innovations are going to be necessary. We still start out with very basic methods in case those turn out to work well. When thinking about climate applications of ML, it's essential to conceive of them as collaborations, including both ML experts and domain experts. Often other stakeholders who are involved in deployment or are affected by the technology should be included too. These kinds of partnerships are important to make sure that the algorithms aren't solving the wrong problem, and that where possible, they leverage domain-specific knowledge. Partnerships are also key in shaping a pathway to impactful deployment and ensuring that any deployment-relevant considerations are built into the design right from the start. Lastly, equity considerations are fundamentally important, including who is building solutions, what problems are prioritized, and how these problems are worked on. Empowering a diverse and global set of stakeholders is essential to ensure that technologies are owned by the people affected by them, rather than reinforcing existing power imbalances across countries and institutions. Related to the question of who is the question of what is being worked on, since problem priorities often reflect existing inequities within ML and technology more broadly. For instance, ML to fight wildfires, which is a key problem in North America, Europe, and Australia, tends to receive more attention and funding than ML to fight locusts, which affect East Africa, the Middle East, and India, even though both problems are extremely important and are exacerbated by climate change. And how problems are worked on is also important. Data imbalances between regions or between communities within a region can mean ML solutions are only applicable to a subset of the population, or that algorithms are most effective within data-rich areas. Ideally, ML for climate will serve to improve equity, but this takes active work at the level of project design and management. Before concluding, I want to discuss how machine learning can also be used in ways that negatively impact the climate. We discussed this in a recent paper in Nature Climate Change, led by my colleague, Professor Lynn Koch, and we highlight three kinds of impact that ML can have. First, there are the computational impacts. This includes the energy used for computation during development, training, and inference. For some LLM models, this energy may be very small, while for bigger models, it can be relatively large. There are also greenhouse gas emissions associated with making the hardware used to run the algorithm. Second, there are the direct impacts of whatever the machine learning is being used to do. For example, machine learning algorithms are used extensively in oil and gas exploration and extraction, which directly results in more emissions. AI and other advanced analytics techniques are estimated to make the fossil fuel industry $500 billion in extra profit just by 2025. And then finally, applications of ML can have more systemic impacts. For example, ML is used in advertising systems to get people to buy more, which is probably significantly increasing global consumption of resources and energy. Autonomous driving, which is based on machine learning, has a complicated set of systemic impacts. It can be either good or bad for the climate, depending on how the technology is developed and used. Personal self-driving cars may make it easier to drive and therefore increase greenhouse gas emissions. But prioritizing self-driving buses and trucks instead might lower greenhouse gas emissions. This example shows how the implicit choices we make in designing a technology can greatly change the impact that it has. Overall, AI for good doesn't mean just adding new good applications of AI on top of business as usual. It also means shaping all applications of AI to be better for society, including the ways that AI is already being used, because those impact society too, whether we like it or not. If you're interested in using machine learning to help fight climate change, there are many more resources available. I co-founded the nonprofit Climate Change AI 3 years ago to help catalyze impactful work at the intersection of climate change and ML. Since then, it's grown into a global community of thousands of people across many different fields and sectors, and there are many ways to engage. Check out our digital resources, reports aimed at researchers, practitioners, policymakers, and other stakeholders, educational materials, and a new community-driven wiki that compiles datasets and other info. Participate in our events, including our upcoming workshop on tackling climate change with machine learning at NeurIPS 2022, the leading research conference in machine learning. You can also check out video recordings and papers from our past events online. Apply for our annual summer school. Applications will open in a few months. Or participate in our Innovation Grants program, which has provided millions in funding for impactful research around the world. If you want to keep up to date on this space, we have a monthly newsletter with listings of jobs, events, grants, papers, datasets, and more, as well as a blog. And if you're looking to meet more folks interested in this space, but can't wait until our next event, we have a digital community platform to ask questions, share information, and find collaborators. We also host regular webinars and happy hours. Thank you all for listening.